Alrighty, trigonometry. So in 20-1, let's take that one at the top, right up there. Yeah. In 20-1, you learned about, well, I guess backing up 10C, you learned about right triangle trigonometry. And then in 20-1, that was extended to oblique triangles, triangles that were not right angled. You learned about the law of sines and the law of cosines, and you were likely introduced to the unit circle in 20-1. So we're going to continue that work with the unit circle in this course, as well as get into some other stuff. We're going to be looking at the graphs of trig functions. We'll look at trig identities and some proofs involving trig identities. And then we'll also be solving some trig equations. Back in 20-1, you learned a little bit about solving trig equations, so we're going to extend that in this unit, right? So this unit will be on chapters 4, 5, and 6, all on trigonometry. And then at the end of chapter 6 will be our next unit exam. Okay? Once everyone has written the exam you guys wrote yesterday, we will go through it. And then there'll be an opportunity for you to rewrite that if you would like. Remember that review assignment needs to be handed in. There's a couple of you that haven't done that yet. So you need to get that done and hand it in so I can get those marked. All right? So, trigonometry. So last year and again grade 10, you learned about angles and standard position. We'll continue that work in this chapter. You also learned about special triangles. By convention, angles measured in a counterclockwise direction are positive rotation angles. If it goes in a clockwise direction, that's a negative rotation angle. In past work, you did most of your work with angles in degrees. 1 degree is defined as 1/360th of a revolution. In order to simplify some calculations involving trigonometry and calculus, mathematicians use an alternative angular measure known as radian measure. So 1 radian is the measure of a central angle subtended in a circle by an arc length that's equal to the radius. So an arc is a portion of the circumference. It's the distance around the edge of a circle. So it's a portion of the circumference. What am I looking for? There it is. So an arc is a portion of the circumference. Okay? So if the arc length is equal to the radius, the angle at the center that will subtend that arc, make that arc, will be 1. That's what this is saying. Okay? If we're talking about the angle at the center, measure in radians now instead of degrees. 1 radian will be the angle at the center where the arc length, r, is equal to the radius of the circle. So that kind of leads us to an equation for arc length, theta. It is the ratio of, I shouldn't say arc length, the measure of the central angle theta, and let's again tell that that is in radians, can be found by taking the length of the arc A and divided by the radius r. And this formula is actually on your formula sheet. The measure of the central angle theta in radians can be found by taking the length of the arc and dividing by the radius. Now, they would need to be in the same units, maybe both in centimeters, maybe both in meters, whatever the case is, right? But that's how we find the measure of the central angle in radians. It's the ratio of the arc length divided by the radius. And again, this is on your formula sheet, so you don't have to memorize it. And so that tells you then if you are using this arc length formula, that theta must be in radians. So this next part says estimate the radian measure of angle AOB and angle POQ. And so it's just an estimate. So, I mean, you could get out a piece of string, measure the length of this arc length using a piece of string, lay that string on that arc, and then compare it to the length of the radius r, and you would see that in this case here, the length of the arc is twice the radius, approximately. All right, so if we're using that relationship again, that theta in radians is the length of the arc divided by r, the radius. Again, if you used a piece of string and compared the length of the radius to the length of the, the length of the arc to the length of the radius, you would see that the arc is approximately twice the radius. So 2r over r. The length of the arc is twice the radius, approximately. And then the r's cancel, and you get an answer of 2. So this central angle is approximately 2 radians. Now, before, when you talked about angles in degrees, they always had that little degree symbol on them. So it told you they were in degrees. When you're given radians or you're talking about a radian measure, you can write the word radians if you want. You can write the word radians or rad, whatever. But also, if you're not given a unit, when you're told that this number is an angle and there's no unit given, that means it's also in radians. If it's degrees, it'll have that little degree symbol at the top. Right? But if it's not, if there's no degree symbol, if it's just a number, that means radians. Sometimes it'll be written radians. That tells you that it's radians as well. But if there is no unit, then that means the angle is in radians. When we're talking about an angle and no unit is given, it's in radians. Now for that second one, that's the same as the one above. The arc length r is the same as the radius because they're both labeled as r. So in this case here, the measure of the central angle would be r over r, or 1 radian. And again, if no unit is given, it means that we are in radians. So we'll begin with 2 basic concepts. 1 complete revolution of a circle is 360 degrees. So once around a circle is 360 degrees. The circumference of a circle with radius 1, and remember that formula for circumference is 2 pi times r. The circumference, remember, is the distance around a circle, 1 complete revolution. And if the radius is 1 unit, knowing that the formula for circumference is 2 pi r, when you let r equal 1 as the radius, you're just going to get 2 pi. So this means that 360 degrees is equivalent to 2 pi radians. Remember that the angle in radians is the angle at the center. And if you don't go 1 complete revolution around the circle, in terms of degrees, that would be 360 degrees. But now we can find that measure in radians by using the circumference formula. Circumference equals 2 times pi times r. And again, if you use that relationship that we had before, theta, the measure of the angle in radians, is a, the arc, over r, the radius. If you're going 1 complete circle, 1 complete rotation around the circle, then the arc length will be 2 pi times r, the radius, because the arc would be 1 complete revolution, and that is the circumference of that circle. The circumference is 2 pi r. If the radius is 1 unit, then r is 1, and we're dividing it by r. Again, the radius is 1 unit. The 1's cancel, and you get 2 pi radians. If you're talking about degrees, 1 rotation is 360 degrees, and now we see that we're talking about radians. 1 rotation is 2 pi radians. So 360 degrees is the same as 2 pi radians. 1 revolution around the circle would be 2 pi radians. So on the next page, again, we know that 360 degrees corresponds to 2 pi radians. If you divide both sides by 2, you will get pi radians equals 180 degrees. 180 degrees halfway around the circle is the same as pi radians. So again, I didn't write a unit beside the pi, which means that it is radians. Now, if you take this relationship and you divide both sides by 2, that'll tell us that pi over 2 radians is 90 degrees. 1/4 around the circle is pi on 2 radians. If you take this relationship and divide both sides by 3, you'll get pi on 3 radians on the right equaling, on the left, 180 divided by 3 is 60 degrees. 60 degrees is the same as pi on 3 radians. If you take this relationship and divide both sides by 4, you'll get pi on 4 radians on the right. On the left, 180 divided by 4 is 45 degrees. So 45 degrees is the same as pi on 4 radians. And finally, if you take this relationship and you divide both sides by 6, you're going to get pi on 6 on the right. On the left, 180 divided by 6 is 30. So pi on 6 radians is equivalent to 30 degrees. But it all comes from the fact that 2 pi radians is 360 degrees. If you divide them both by 2, you'll get pi radians equals 180 degrees. And then from there, divide both sides of this relationship by either 2, 3, 4, or 6 to get the other ones. But it all comes from the fact that 2 pi radians is 360 degrees, or pi radians is 180 degrees. So let's start talking about this unit circle. You saw it back in 20-1 along with those special triangles. But the key to the unit circle is that it has a radius of 1. A unit circle is a circle with a radius of 1 unit. So we've got this template below. We want to fill in the measures of the rotation angles in both degrees and radians. This is just an introduction, or if you want a review, because you would have seen this in 20-1 of the unit circle, as we go around in angles in terms of degrees as well as in terms of radians. So we start here, all our angles start in standard position, which means that you're starting on the positive x-axis, right? You can think of this as an xy axis. This is the positive x-axis there. So starting at 0 degrees. So let's do degrees first. 1/4 of the way around the circle would be 90 degrees. Halfway around the circle is 180 degrees. Another quarter turn would take us to 270 degrees, and then back up here you're at 360 degrees. One complete rotation around the circle. So that's going around the circle in terms of 90 degrees. We can also go around the circle in terms of 45 degrees. Halfway between 0 and 90 is 45. So this takes us to 45 degrees. Another 45 takes us to 90. Another 45 would be 135 degrees. Whoops. Another 45 takes us to 180. 45 degrees past 180 is 225 degrees. Another 45 takes us to 270. Another 45 takes us to 315 degrees. So that's going around the circle in terms of 45 degrees. Next, let's go around the circle in terms of 60 degrees. 60 is just past 45. Another 60 would take us to 120, which is between 90 and 135. Another 60 takes us to 180, which we already have. Another 60 past 180 takes us to 240. So that's past 225, between 225 and 270. Another 60 takes us to 300 degrees. So that's just short of 315. And then another 60 degrees past 300, we're back to 360. So those are the stops along the unit circle if we're going around in terms of 60 degrees. And the reason we're using these angles is because of what we have above. 90 degrees corresponds to pi on 2 radians. 60 degrees corresponds to pi on 3 radians. 45 degrees corresponds to pi on 4 radians. So that's why I went around in terms of 90, in terms of 45, in terms of 60. The last one is 30 degrees. That corresponds to pi on 6 radians. So if we go around the circle in terms of 30 degrees, the first stop will be 30 degrees. Another 30 takes us to 60, which we already have. Another 30 takes us to 90, which we already have. Another 30 takes us to 120, which we already have. But another 30 will take us to 150, which is between 135 and 180. Another 30 takes us to 180, which we already have. Another 30 takes us to 210, which is between 180 and 225. Another 30 takes us to 240. Another 30 takes us to 270. Another 30 takes us to 300, which we already have. Another 30 takes us to 330, which is between 315 and 360. And then another 30 takes us to our 360. So this is nothing new for you, going around in multiples of 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees. That should all be familiar to you. But now we're going to go around in terms of radians as well. So we'll start here with 0 or 0 radians. Remember, if you don't have a unit, it means it's in radians. So let's first go around in terms of 90 degrees, which we know is pi on 2 radians. So 90 degrees is pi on 2. And again, when an angle is measured in terms of pi as a multiple of pi, that also tells you that you're dealing with radian measure. If an angle is stated in terms of pi, you don't, again, need any unit to tell you it's radians. But when it's in terms of pi, that's another reason why you're talking about radians. So 90 degrees is pi on 2 radians. If we go another 90 degrees, that takes us to 180. That's another pi on 2, which will be pi radians. And we saw that above. Halfway around the circle is pi radians. So again, that's also can be expressed as 2 pi on 2s. We want 1 pi on 2 up at 90. 2 pi on 2s would take us to 180, and the 2's cancel. You're left just with pi. Another pi on 2 would take us to 3 pi on 2. 3 pi on 2 is equivalent to 270 degrees. And another pi on 2 would take us to 2 pi radians. Again, that's equivalent to 360 degrees. Once around the circle is 360 degrees. And if the circle has a radius of 1, that's a unit circle. Once around is 2 pi radians. Now let's go around the circle in terms of pi on 4 radians, which is equivalent to 45 degrees. So 1 pi on 4 is 45 degrees. Another pi on 4 would be 2 pi on 4s, which is what pi on 2 is. Another 45 degrees from 45 takes us to 90. Another 45 from 90 takes us to 135. At 90 degrees, we were at 2 pi on 4s. So one more will take us to 3 pi on 4 radians. Another pi on 4 takes us to 4 pi on 4, which is pi. Then 5 pi on 4, it's another 45 degrees from 180. Gives us another pi on 4 from 4 pi on 4, that's 5 pi on 4. Another 45 degrees from 225 takes us to 270. That's another pi on 4 from 5 pi on 4. That'll give us 6 pi on 4. And 6 pi on 4 reduces to 3 pi on 2. Another 45 degrees from 270 took us to 315. That's another pi on 4 from 6 pi on 4. which is 7 pi on 4. And another pi on 4 from 7 pi on 4 takes us to 8 pi on 4, which is 2 pi. So again, 7 pi on 4 is equal to 315 degrees. And we're going to talk about converting from radians to degrees and then from degrees to radians. There's almost always a question on the diploma exam where you have to do that, usually a multiple choice question. Right? But remember, we said that pi radians was equal to 180 degrees. So if I take this angle of 7 pi on 4, for example, and I want to show that that is equal to 315 degrees, well, remember, pi radians is 180 degrees. So if I take 7 pi on 4 and I convert that to degrees, I can do it by letting pi radians equal 180 degrees. It's 7 times pi, which is 180, divided by 4. 7 pi on 4 is 315 degrees. You can do that conversion because we know that pi radians is 180 degrees. So we've gone around the unit circle in terms of pi on 2 radians and also in terms of pi on 4 radians. Now let's go around the circle in terms of 60 degrees, which is pi on 3 radians. Again, pi is 180. 180 divided by 3 is 60. That's why pi on 3 is equivalent to 60 degrees. So another 60 degrees, which would take us to 120, would be another pi on 3, which would be 2 pi on 3. Another 60 degrees from 120 would be 180, and that's 3 pi on 3. 3 pi on 3 is pi. Another 60 degrees from 180 would be 240. That would be 4 pi on 3s. And again, just to show that 4 pi on 3 is equivalent to 240, you can convert by letting pi equal 180 degrees. 4 times 180 divided by 3 gives you your 240 degrees. That shows you that 4 pi on 3 is the same as 240 degrees. So from 240, another 60 would be 300. It's another pi on 3 from 4 pi on 3 takes us to 5 pi on 3. And then another 60 degrees will be 360. That would be another pi on 3. That would be 6 pi on 3s, which is equal to 2 pi. So that's going around the circle in terms of pi on 3s. So finally, let's go around the circle in terms of 30 degrees, which is pi on 6 radians. 180 divided by 6 is 30 degrees. So that's why pi on 6 is equal to 30. Another 30 would be 60, which is 2 pi on 6s. 2 pi on 6 reduces to pi on 3. Another 30 from 60 is 90. That would be 3 pi on 6s, which reduces to pi on 2. Another 30 would be 120, which is 4 pi on 6s, and that reduces to 2 pi on 3. Another 30 from 120 would be 150. That would be 5 pi on 6s. Another 30 would take us to 180, which is 6 pi on 6. That reduces to just pi. Another 30 from 180 takes us to 210. That would be 7 pi on 6s. Another 30 from 210 would take us to 240. That would be 8 pi on 6, which reduces to 4 pi on 3. Another 30 from 240 would take us to 270. That would be 9 pi on 6s. And that reduces to 3 pi on 2. Another 30 from 270 would take us to 300. That would be 10 pi on 6s, which reduces to 5 pi on 3. If you divide top and bottom by 5 there, top and bottom by 2, you'll get 5 pi on 6. Another 30 from 300 would take us to 330, which would be another pi on 6 past 10 pi on 6. One more would be 11 pi on 6s. And again, we can show that that is equivalent to 330 degrees by taking our calculator and remembering that pi radians is 180 degrees. So 11 pi on 6 would be 11 times 180 divided by 6. 330 degrees, same thing. And one more pi on 6 past 11 would be one more 30 degrees past 330, takes us to 360. That is 12 pi on 6s, which reduces to 2 pi. Okay? So that's how we go around the circle in terms of degrees as well as radians. Remember, a positive direction, which we did here, is a counterclockwise direction. We will do some work where we're going to have negative rotation angles. We'll see that on the next page. When the rotation angle is negative, that means you're going clockwise. That many degrees or that many radians. So again, we've seen that 180 degrees is equal to pi radians. We just use that to convert some of those angles from radians to degrees. When an angle in radians is expressed in terms of pi, you can let pi equal 180 to convert it to degrees. But not all radian measures are expressed in terms of pi. Sometimes you'll be given an angle just 2 radians, or 1.5 radians, or negative 3.6 radians. And you got to know how to convert that into degrees. You're going to have to know how to convert from radians to degrees as well as from degrees to radians. One of the applications where you will have to convert from degrees to radians is using the arc length formula that we talked about at the start of today. A, the arc length, is the ratio, theta, the central angle in radians, is the ratio of the arc length over the radius. And to do that, theta is in radian measure. So if you're asked to determine the length of an arc, but they give you the measure of the central angle in degrees, the first thing you must do is convert that angle into radians. When you're using that arc length formula, that theta equals A over R, arc length over radius, theta has to be in radians. So if it's given in degrees, you'd have to convert it to radians before you use that formula. So how do we convert from degrees to radians and radians to degrees? Well, again, we know that 180 degrees is equal to pi radians. If you take that expression, that equation, and divide both sides by 180 degrees, you're going to get 1 degree, because on the left, 180 divided by itself is 1. 1 degree is equal to pi over 180 radians. So if you have an angle in degrees and you want to convert it to radians, all right, for example, let's say you had 25 degrees and you wanted to convert that to radians. So if we take that expression right there and you wanted to know what 25 degrees is in radians, you'd multiply both sides by 25. 25 degrees would be 25 pi over 180 radians. You'd multiply both sides by 25 degrees to get 25 degrees on the left. So to convert from degrees to radians, you multiply by pi, you take the angle in degrees, multiply by pi, and then divide by 180. So because you're multiplying by the angle, which in this case is 25, and dividing by 180, your answer will get smaller. Yes, you're multiplying 25 by pi, which is approximately 3.14, so that's just something over 75 degrees, but then you're dividing by 180. Your answer is going to get smaller. The number of radians will always be a number that's smaller than the number of degrees, because you're going to multiply the angle in degrees by pi, but then divide by 180. So your answer will get smaller. The number of radians is always less than the number of degrees. Okay, now, if you want to go from radians to degrees, we start with the same expression. Pi radians is equal to 180 degrees. To get 1 radian, you would divide both sides by pi. So 1 radian is 180 divided by pi. So if you're going to go from radians to degrees, let's say you had 2.5 radians and you wanted to convert that to degrees, well, you need this 1 to be 2.5. You'd get it by multiplying by 2.5, and you'd multiply the right side by 2.5 as well. So to go from radians to degrees, you take the angle in radians, multiply by 180, and then divide by pi. That's going to make the number become larger because you're multiplying by 180. Yes, you're dividing by pi, which again is approximately 3.14, but you're multiplying by 180, which is much larger. So the number of degrees will always be a number that's greater than the number of radians. So when you're converting, you're either multiplying by pi and dividing by 180, or the reciprocal, you're multiplying by 180 and divided by pi. When you're going from degrees to radians, your answer has to get smaller, so you're going to multiply by pi and divide by 180. If you're going from radians to degrees, your answer has to get bigger, so you're going to multiply by 180 and divide by pi. And that's what it says in that chart. This is not on the formula sheet. Okay, you need to remember this. It's either multiplying by 180 and dividing by pi if your answer has to get bigger, which means you're going from radians to degrees, or you're multiplying by pi and dividing by 180, which means your answer has to get smaller, which you would use if you're going from degrees to radians. Okay, however, if your angle in terms of radians is in terms of pi, then you can do the conversion just by letting pi equal 180, like we saw before. But not all angles in radians are written in terms of pi. Like I said, you can get 1.5 radians, or 2.6 radians, or negative 3.8 radians. In those cases, to go from radians to degrees, again, your number will get larger, so you must multiply by 180 and then divide by pi. So this example says, draw each angle in standard position. Change each degree measure to radian measure, and each radian measure to degree measure. Give answers as both exact and approximate if necessary to the nearest hundredth. So what does this look like? Well, the first angle is 30 degrees. Again, that is a positive rotation angle. So we need to go counterclockwise 30 degrees, which would take us to approximately there. This is that rotation angle. You're going positive 30 degrees, you're going counterclockwise 30 degrees. And if you want to write that in terms of radians, again, your number must get smaller. So we would multiply by pi and divide by 180. And that expression can be reduced by dividing top and bottom by 30, which gives us pi on 6 radians, which we just saw. We just saw that on the previous page, that 30 degrees was the same as pi on 6 radians. Now the next one, you're going negative 120 degrees. You're going 120 degrees in a clockwise direction. So you're going to go 90 and then 30 degrees past there to get to 120 in a clockwise direction now. Right, so our rotation angle, try that again. Our rotation angle will look something like that. That's a rotation angle of negative 120 degrees. And if we want to write that in radians, again, your number must get smaller. So we'll multiply by pi and divide by 180. And in this case, you can reduce by dividing top and bottom by 60. And we'll get negative 2 pi over 3 radians. Negative 120 degrees is the same as negative 2 pi on 3. And once again, if you wanted to check that, remember, let pi equal 180. Negative 2 times 180 divided by 3 is negative 120 degrees. So again, there's always a question on the diploma exam where you got to convert either from degrees to radians or radians to degrees. Usually it's a multiple choice or a numerical response, but you should be prepared for that. 5 pi on 4 radians. So this is a positive rotation angle. You need to go in a positive direction, 5 pi on 4 radians. So you should recognize that this is 1 pi on 4 past 4 pi on 4. 1 more pi on 4 from 4 pi on 4 is 5 pi on 4. And 4 pi on 4 is pi. We have to go 1/4 pi past pi. 1 pi on 4 past 5 pi, 4 pi on 4, excuse me. And 4 pi on 4 is pi. So we go counterclockwise, 1/4 pi past pi. It's going to be right there, approximately. You might remember that just pi on 4 was halfway between 0 and pi on 2, or between 0 and 90 degrees. Okay, so that's where we are. Now, if we want to convert that to degrees now, because this is in radians, the way to do that is to, again, let pi equal 180 degrees. Because the angle is in terms of pi, if we want to convert it to degrees, we will let pi equal 180 degrees. So it'll be 5 times 180 divided by 4. 225 degrees. And we saw that on the previous page when we filled in those angles. 225 degrees is the same as 5 pi on 4 radians. Okay? But that's where it comes from. The next one, that is in radians because there's no unit indicated. It's in radians. And we want to go positive 2.57 radians, which would be, again, in a counterclockwise direction. And we can guesstimate where that is before we turn it to degrees, because pi radians would be the same as 3.14 radians. Remember, pi radians is halfway around the circle, and the value of pi is approximately 3.14. So pi radians would be halfway around the circle. That's approximately 3.14 radians. We're going to be a little short of that. 2.57 is a little bit before 3.14. So there's a rotation angle approximately 2.57 radians. A little bit less than 3.14, which is pi, which is halfway around the circle. Do you have this booklet?
Yeah.
Okay, so we are on page number 4. Now, if you want to convert that to degrees, our number must get larger. The number of degrees is always a bigger number than the number of radians, which means we're going to have to multiply by 180 and then divide by pi to convert that measure into degrees. So get our calculator to do that. And I need to fix that because I didn't get the decimal in there. 2.57 times 180 divided by pi. And use the pi button, because that's going to give you a more accurate answer to round. Don't just use 3.14. Always use exact values if possible. So we can see that's approximately 147.25. It says if you're going to approximate, round to the nearest hundredth of a unit, 2 decimal places. So approximately 147.25 degrees. approximate symbol here. And because it's degrees now, we need to make sure we use that unit, that degree symbol. So last thing we're going to talk about today are coterminal angles. Those are angles in the standard position that have the same terminal arms. So what does that mean? So example 2 says determine one positive and one negative coterminal angle for each of these, and also what quadrant does the terminal arm lie in. The first one is 40 degrees. So 40 degrees would be approximately there, a little bit less than 45 degrees. If we want to get coterminal angles to 40 degrees, coterminal angles are angles that have the same terminal arm. So to rotate and end up in the same spot, you're going to have to rotate 360 degrees. It's possible to have rotation angles that are larger than 360 degrees. The very next question has an angle that's less than negative 360. So you can go around the unit circle as many times as you need to. You don't have to stop after one revolution. So again, coterminal angles are angles that have the same terminal arm. To get there, you have to do one complete rotation from where you are. So that could be done by going around 360 degrees in a positive direction, which means you would add 360 degrees onto 40. So 40 plus 360 degrees is 400 degrees. And to get a negative rotation angle that's coterminal to 40, you would have to subtract 360. You'd have to go 360 degrees in a negative direction, which is a clockwise direction. So that would be 40 minus 360 degrees, which would be negative 320 degrees. Those are the first positive coterminal angle as well as the first negative coterminal angle to 40 degrees. You end up at the same spot on the unit circle. And so what that means then, and you can use this to check to make sure that the angles you get are in fact coterminal. You can check that by using the calculator. In this case, we need to be in degree mode because our angles are in degrees. When we're dealing with an angle in radians and you're doing some sort of trig calculation, you must be in radian mode. But right now, these are angles in degrees, so we are in degree mode. And you see, if you take either the sine or the cos or the tan of 40 degrees, in this case, let's just do the sine of 40 for no reason, except that's the first one. That should equal the sine of the two coterminal angles that we found. It should equal the sine of 400. And it should equal the sine of negative 320. And they do. This tells us that the numbers we came up with for coterminal angles to 40 degrees are correct. If you did the cosine of 40, you'd get a different decimal. But you get the same decimal for the cosine of 400 and the cosine of negative 320. Same thing with the tangent. The only time it wouldn't work is if you got a value that was a non-permissive value. For example, if we were dealing with 90 degrees as our original angle, and you took the tangent of 90, you'd get an error. Tangent of 90 doesn't exist. Okay. And we'll see why that is true when we get to the graphs of the trig functions in chapter 5. So the only angles it wouldn't work for would be an angle like 90 degrees, and only if you were doing tangent, because the tangent of, the sine and cosine of 90 degrees does exist, just not the tangent of 90. Okay, so the next one, we need to start with a rotation angle of negative 430 degrees. That means we're going clockwise 430 degrees. So we're going to go one complete revolution, which would be negative 360, and then we're going to go past that. So that shows a rotation angle of negative 360. Now, if we went another 90 degrees from negative 360, that would take us to negative 450, which is too far. So we need to back up a little bit. Instead of negative 450, we need to be at negative 430, so that would be approximately there. So there's negative 430 degrees. One complete revolution in a clockwise direction plus a little more. So now we want to state the angles that are coterminal with that. Well, the first negative coterminal angle, you could subtract another 360 and that would work. Or we could also add 360 degrees. That would take us 360 degrees in a counterclockwise direction, and it would still give us a negative angle. So that would be negative 70 degrees. And if I take that negative 70 degrees and add another 360, that would be positive 290 degrees. So I've got a negative coterminal angle as well as the first positive coterminal angle. And to check it, let's take the cosine of negative 430. That's the angle we started with. It's that decimal. That should be the same as the cosine of negative 70 and the cosine of 290. All the same decimal. That means that these angles are both coterminal with the original. They're the same angle. Take you to the same spot on the circle. The question also asks us to state the quadrant we're in. That's the first quadrant. And you work your way counterclockwise around. And the reason that the quadrants are numbered in this way, I don't know if I told you or not, but when mathematicians first started developing the principles of trigonometry, they started looking at how the sun goes across the sky. And the sun rises in the east and sets in the west. So that's why they started with quadrant 1, starting in that quadrant, because that's where the sun first appeared, and then it disappeared after quadrant 2. So that's why they labeled the quadrants the way they're labeled. It's the way the sun moves across the sky. Now for this last one, the angle is in radians, right? 8 pi on 3 radians. This is a positive rotation angle, so we are going counterclockwise, 8 pi on 3s. So to do this one, you need to remember that once around the circle is 2 pi radians. That would be the same as 6 pi on 3s, because 6 divided by 3 would give you the 2. So 2 pi radians would be the same as 6 pi on 3. So once around the circle would be 6 pi on 3. And it's also helpful to remember that when you're talking about pi on 3, that's the same as 60 degrees, because 180 divided by 3 gives you 60. So this is 6 pi on 3. I need to go 2 more pi on 3s, or 2 more multiples of 60. Take us approximately right there. So that's where we are. In this case, we are in quadrant 2. In the previous example, we were in quadrant 4. Now, 8 pi on 3 is where we're at. So if I want to get another positive coterminal angle, I could either add 2 pi, which is adding 6 pi on 3's, or in this case, I could subtract 2 pi. I could subtract 6 pi on 3's. And the reason I'm using 6 pi on 3 is because 6 divided by 3 is 2. That's the same as subtracting 2 pi. And the reason 2 pi is used because 2 pi is 1 revolution around the circle. So this will give us 2 pi on 3's. There's a positive coterminal angle. And I'll get my negative 1 by subtracting another 6 pi on 3, which gives us negative 4 pi on 3. So there's our two coterminal angles, one positive, one negative. There are infinitely many coterminal angles you can come up with. I'm just always coming up with the ones that are closer to 0, or closest to the angle we started with. And again, we can check these in our calculator, but now because our angles are in radians, we need to be in radian mode. And for no reason, I'm just going to use the tangent in this case. The tangent of 8 pi on 3. So again, you must use the pi button here. Is that value. If I take the tangent of 2 pi on 3, it's the same decimal, and the tangent of negative 4 pi on 3. Same decimal. So the angles that we came up with for coterminal angles are correct. We just checked them. Okay? So we'll stop there for today. We're going to work on those questions. I will post the solutions to Google Classroom so you can check your answers. Okay? Some of you may be a little disappointed in how you did on that exam. That should tell you that you need to work harder. Okay? No one said this was an easy class. It's not. The fact that you guys all survived 20-1 tells me that you should be able to survive this as well. You may have to work harder though. So if you're not getting the marks that you want, work harder. Not all of you handed in that review assignment. That tells me that not all of you had it done before the exam. Right? If you were having trouble on that, you'd have had those same troubles on the questions on the exam. Right? So for this next unit, make sure you get that review assignment done prior to the exam so that you get everything cleared up before you write that exam. Okay? And duly practice. That's what the homework is practice. I said this at the start. Math is no different than music or sport. You need to practice to get good at it. You all can't be natural athletes like myself or natural mathematicians. And that's not true either. I had to work hard. I wasn't a gifted math student when I was in high school. I wasn't. When I started teaching math, I was actually a phys ed major. I was supposed to be a phys ed teacher. But when I graduated, there were no phys ed jobs available. Math was my minor, so that's where I started teaching. And it was a lot of work to get a handle on everything, right? So do the work and you'll get rewarded. All right?